Hi guys, it's Daniel here, and since the AMC A and B are over, it's time to start some AME prep. And for today, I'm actually going to do an AMC 12 problem as AME prep. This is going to be problem 18 from the 2012 AMC 12B, I believe. So let's get started and read the problem. Let A1, A2, all the way to A10 be listed the first 10 positive integers such that for each 2 is less than or equal to I less than or equal to 10, either AI plus 1 or AI minus 1 or both appear somewhere before AI in the list. How many such lists are there? So first, if we want to solve the problem, of course, we have to first understand what the problem is saying. So let's read carefully and try to figure out what exactly this problem is saying. So let's say we have a list of numbers, and let's say that 2 is somewhere in the middle right there. What this problem is saying is that either 1 and or 3 is going to be somewhere before the 2 in this list. And this is going to be true for anything. For example, for 4, either 3 or 5 is going to be somewhere before the 4. And then this is true for all the numbers 1 through 10. And with the exception, of course, of the very first number on the list, which has no numbers before it, so there's no problems there. So now that we know what the problem is saying, let's try to solve the problem. So in order to solve this problem, let's think about what exactly we're building with our list. So let's start with the first number. Okay, so the first number can be anything. As far as we know. 3, let's say. Okay, well that's all nice and fair, but things kind of get a little bit murky afterwards, because that means that we can either put like a 4 or a 2 here, and then maybe we can put, say, either like a 1 or 3 here, but 3 is already there, so we can either pick a 3 or a 5 here. Okay, and then we can either pick a 4 or let's say a 6. Okay, and do you guys sort of see what is happening right now? Well, let's think about this a little bit in a little bit of a different way. So we start out with a number. Okay, let's just say we start out with a number, and I'll write the list of all the numbers that we will use. Okay, so we have a list of numbers. So we start out with a number, and afterwards, for every single number afterwards that we choose, that number has to be it has to be adjacent to one of the numbers that we already have on the list. For example, at this point, if we chose 3, then 2, then 4, then the next number has to be either 1 or 5. It has to be something adjacent to a number that was previously on the list. So if we represent this as filling in or check marking which numbers we've already used in this little grid that I've made right here, let's say we start with 3, then we can either choose to add 4 or 2. Let's say I add 4, and then let's say that we can now choose either to add 2 or 5 because they have to be adjacent to either 3 or 4. So let's say I choose 2. Now at this point I can choose either 1 or 5. So okay, I might choose 5, then I might choose 6, then I might choose 1, and then at this point everything else is forced, because I can't add 8 before I add 7, since that would violate this condition. Either AI plus 1 or AI minus 1 both appear somewhere before the list. So therefore I must add 7 next, then 8 next, then 9 next, then 10 next. So do you guys now sort of see what's happening with this problem? The idea is that we start out with a single number that we choose, sort of seed, I guess you can call it, and then after that we successfully fill adjacent squares until we have everything filled out. So how exactly can we count how many ways we can do this? Because it's clear that the number of sequences that we have is going to equal the number of ways that we can fill this grid of 10 squares out using check marks, such that every single check mark is adjacent to a previous check mark. Well, we could do it in a forward direction. We can choose first which cell we take, and then, okay, there's two choices on left or right, and then there's two choices, then there's two choices, still two choices, but once we fill in one of the ending numbers, there's only one choice left. And we don't know when we're going to fill in the ending number, so it's a little bit unclear about how we might count this. It is possible, and with a little bit of thinking, you can figure out how to count it in this way. But there's a slightly easier way to do this, and the slightly easier way is to count backwards. Suppose that we already have all 10 check marks in the board, and we're going to reverse time and start to erase the check marks. How many distinct ways can we erase these 10 check marks, such that we either erase the one on the left or the one on the right? Well, it's clear that every single move, we can either choose the left check mark or the right check mark to erase. That means that every single move we have two choices. And how many moves do we have? Well, after we move 9 times, there's going to be one check mark left, which we have to erase. So we're going to have 9 choices of either the left or right one to make, which means that there's a total of 2 to the power of 9 different ways we can erase these check marks from the grid, which means that there's 2 to the 9 different ways to create a sequence such that it follows this rule. And 2 to the 9 is 512, so that is our answer. So this is all a good solution, but the solution is a little bit difficult to come up with, perhaps. It's certainly not obvious that in order to solve this problem, we might want to consider it in a sort of graphical fashion. So say that you didn't think about this, and you're totally stuck on this problem. How might you solve it? Well, you might just decide to give up and go to the next problem. However, for this type of problem, there's a very special technique that you can also use. And this technique works not only for multiple choice problems, but for short answer problems as well, hence why I'm talking about it right now, even though the AMCs are already over. Because you can use this technique on AMY problems. And this technique is called engineer's induction. So what is engineer's induction? Normal induction is where you start out with a base case, which you prove, and then you prove that if this statement for n is true, implies the statement for n plus 1 is true. If that's always the case, then that means the statement must be true for any n that we choose. Because it's like a sequence of falling dominoes. Once we push down the first domino, then all the other dominoes will fall as well, given that we know that if we push down the nth domino, then the n plus 1th domino will also fall. However, engineer's induction is basically the same as normal induction, except for we don't actually prove that for any n, if the nth domino falls, then the n plus 1th domino falls. What we do instead is we take a look at the dominoes, and we see that, oh, well, the first, second, and third, and fourth dominoes all fell, so I'm just going to assume that the rest of the dominoes will also fall. In other words, it's a strategy about pattern finding, because we find a pattern for the first few dominoes, and then after we find this pattern, we assume that this pattern is true for all the other dominoes as well, even without proving it. And since, of course, the AMY and the AMC are both short answer tests, we don't need to prove it, so we can use engineer's induction perfectly fine. So let's try to use engineer's induction for this problem. So we start out with, okay, well, first off, we should probably figure out what we should induct on. And in this case, let's induct on the number of numbers in our sequence. In this case, our final number is 10, so let's start out with a simpler number. How about 1? How many ways are there to arrange one number of the first 1 positive integers such that this condition is true? Well, there's only one way to arrange one number in general, and certainly for this arrangement, the condition is true because it's trivially true. So there's one way. Now let's go on to a list of 2 numbers, 1 and 2. How many ways can we arrange 1 and 2 such that the condition is true? Well, the condition is always going to be true for both of the arrangements of 1 and 2, so there's 2 ways. Now let's do 1, 2, and 3. It's a little less clear about how many ways we can do it now, so let's just list it out. So I'm going to list out all 6 different ways to... That 3 looked kind of bad. I'm going to list out all 6 ways that we can arrange 1, 2, and 3. 2, 3, 1, 3, 1, 2, 3, 2, 1. Okay, and now let's check each one whether it satisfies the condition or not. Okay, well, for the first one, for 2, okay, so 1's before it, so that means it's fine. And for 3, 2 is before it, so that one's fine. So that means everything is fine. Now let's consider 1, 3, 2. For the 3, is 2 before it? Nope, it's not before it, so this is not fine. For 2, 1, 3, is 2 before the 1? It is. Is 2 before the 3? It is, so this is fine. For 2, 3, 1, is 2 before the 3? It is. Is 2 before the 1? It is, so this is fine. For 3, 1, 2, is 2 before the 1? No, it isn't, so this one is not fine. And finally, for the last one, is 3 before the 2? It is. And is 2 before the 1? It is. So this one's fine. So there's a total of 4 different ways we can do it if there were 3 elements. Do you guys already see this pattern that's forming right now? It seems to look like our pattern is powers of 2. For 1 element, there's 1 way. For 2 elements, there's 2 ways. For 3 elements, there's 4 ways. So we propose that in general, for n elements, 1, 2, all the way to n, there's going to be, if we follow the pattern, 2 to the n minus 1 ways. And you can verify that this formula works for 1, 2, and 3. So, of course, we don't need to prove it because we're using engineer's induction. So we can just plug in n equals 10 to get that the answer should be 2 to the 10 minus 1, which is 2 to the 9, which is 512, which turns out to be one of the answer choices. So we choose it and move on with our lives. So for this problem, there is a very clever combinatorial solution by considering this a little bit more graphically. However, the main point of this video is to show that there's also a sort of cheating strategy called engineer's induction that can get you answers to problems that you don't actually know how to solve. Hi guys, it's Daniel here, and today I'm going to talk about a really special series of nested roots. So first off, what is a nested root?